don't have any questions about this project.
I don't understand. What do you mean? If you don't have any questions, then do it. Right or wrong, man. No, the notes though are important for your test though. So even if you know what you're doing, stick with me on the notes here. All right, so like I said, let's wrap this out real quick, and then I'll give you the rest of class today on your project. If anybody's at home, make sure you select your element and spend some time on your element today. All right, let's carry on. So this unit is on the periodic table. A lot of the things you did on the last unit covered the periodic table too, so hopefully a lot of it is reviewed. And let's see what we got. So we already talked a little bit about elements. The elements are as simple as you can get on matter. And so there's lots of different ways that people named elements. Some of them have been around before we even knew what elements were. Things like sulfur, tin, carbon, and copper. You know, those things had names before we even understood that they were elements, that they were pure. Hey there, Daniel. Some elements came later and were actually named after places. Sometimes they were named after places where the people who discovered them were born. Sometimes they were named after the place where they were discovered. So let's look at some examples of that. What place are we talking about? France, francium. Any guesses? Poland for polonium. Exactly, good job. That's an easy one. Germany, germanium. That's a tough one. Nah, good try though. It's gallium, and it's named for Gaul, which is the south of Spain. That's an easy one. The whole continent of Europe, europium. Americium for America. Californium for California. That's a little bit tougher.
South Carolina.
Now, good try. It's actually scandium for Scandinavia. All right. Sometimes they're named after famous people, especially a lot of the ones that were recently discovered have been named after famous people. Einsteinium for Einstein. This is named for Enrico Fermi. Fermium, more of a physicist. This was named after the guy who first set up the periodic table. His name was Dmitri Mendeleev. It's Mendeleevium. They has an award that they give out every year in Europe for him. You go and win the Peace Prize. You win the what Peace Prize? Yeah, the Nobel Peace Prize. Nobel, Alfred Nobel, Nobelium. Lawrencium for scientist named Lawrence. There's a scientist we talked about. Yep, he was on the jam board. Ernest Rutherford, Rutherfordium. That guy was on the jam board too. Niels Bohr, Bohrium. All right. Sometimes we get our name from foreign languages. That's why you get some weird things. So you get W is tungsten, iron, gold, silver, lead, tin, and copper. Those all have weird symbols because their symbols came from their foreign language name rather than their English name. And then every once in a while you get some mythology related names. That's kind of fun. Yeah, TH is for Thor. Thorium or thorium, depending on who you talk to, but name for Thor. Anybody ever heard of Prometheus? Promethium. This is named for Tal, which is actually a Norse god, Talium. And then before the Greek gods, you had the Titans, titanium. And then Paladin was also a Greek god, Palladium. And then you have some that just are named for what they do. Hydrogen, which is Mercury, and Xenon, which have their special names. So just lots of different reasons to name things. Who gets credit for the first guy doing this is this crazy looking dude up here, Dmitry Mendeleev. Dmitry Mendeleev was Russian, and around 1870, he was the first guy who said, if I start putting elements in order, their properties begin to repeat. Because remember, what word means repeating? Well,
Periodic.
periodic. Periodic means repeating. And so he realized that if he put elements in order of their size, their properties would start repeating, and he did it by atomic mass. Now, is our periodic table arranged by atomic mass? Okay, what is the atomic mass up there? The red number or the blue number? It's the red number. So, sort of is the best answer for that. Because, yeah, for the most part, 1, 4, 6.9, 9.0, 10.8, it goes up in order of atomic mass, but then you get some exceptions. Look at number 52 and 53, tellurium and iodine. Tellurium has a mass of 127.6. Iodine has a mass of 126.9. The mass actually goes down. And so arranging by atomic mass was good up to a point, but it's not perfect. And so a few years later, much more normal looking dude, Henry Moseley, put the elements, instead of increasing atomic mass, increasing atomic number, which is the number of what? Very good. Number of protons. Number of protons arranges your periodic table perfectly. And so Mendeleev's periodic table looked a little bit different. It wasn't like what we have now. The modern periodic table came about 50 years later with Henry Moseley. It made the greatest cheat sheet in the history of science. So we already talked about this a little bit. Periodic law, the properties of the elements repeat. That's why it's called periodic table. The elements repeat. It's periodic. A period, a row, or a column. 50-50 shot. A period is a row or a column. Nope. It's a row. Here's how you can always remember it. You'll always remember it because where do you write a period? At the end of a what? A sentence. And as long as you're in the United States and not in Japan, how do you write a sentence? Left to right on a flat line, right? Periods go from left to right. Okay? So periods go from left to right. How many of them are there? 7. Very good. Not 9. There are 7 periods on the periodic table. You gotta do that. All right? 7 periods on the periodic table. All right? Then you have, from left to right, you have groups or families. How many groups or families are there? What? Nah, way more than 4. I say groups go from left to right. They're actually running up and down. Sorry. 18, exactly. 18 vertical columns, 18 families. And remember, all those elements down there at the bottom all exist in family 3. So where the stars are, all of those elements at the bottom all exist in group 3, family 3. All right? Metals are going to be on the left side of the periodic table. Non-metals are going to be on the right side of the periodic table. You know metals by their properties. They have shared properties. Lustrous, shiny, ductile, malleable. They're good conductors. If you can see, you can barely make it out up on my periodic table up there. If you look at the periodic table on your computers, you get this really nice line between the left and the right, and it's not in the middle. It's a stair-step line that starts at number 5, boron, and goes down to number 85, astatine. You see that like faint stair-step line that I drew up there years ago? That's the line between the metals and the non-metals. Everything to the left of that line is a metal. Everything to the right of that line is a non-metal. If you look on your yellow sheet, hold it up for me, bud. If you look on your yellow sheet, there is a darkened stair-step line right where I'm talking about. Everything to the left of that line is a metal. Everything to the right of that line is a non-metal. So most elements are metals. Non-metals are good insulators. They're opposites. They're brittle. You have neon, sulfur, iodine, bromine. All those guys are non-metals. And then you have guys in the middle. If they're not a metal and they're not a non-metal, they exist right here in the middle, and they're metalloids. Metalloids can sometimes act like metals and sometimes act like non-metals. So look at our examples here. Boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. Now, maybe you hadn't heard of those too much, but I bet you've heard of this one, silicon. Right? Not silicone. Silicone is where, like the plastic, where they make like a silicone, like rubbery thing. But silicon, the metalloid, very good. Okay, they have Silicon Valley in California. Silicon Valley is called Silicon Valley in California because that's where you find what businesses? Yeah, Facebook, Google, Pixar, Apple. All of those guys exist there in California in Silicon Valley because they're making computers and software. So let's think about why silicon works really good for making computers. And it has to do with the fact that it's a metalloid. Okay? Let's think about, take a break from chemistry and think about computers. Does anybody know the language a computer talks in? Code, specifically binary code. You don't, a computer doesn't talk with the alphabet. Yes, it can translate its language into the alphabet, but a computer, when it's talking to another computer, is talking ones and zeros, binary code, two things. It's either a 1 or it's a 0. So instead of A, B, C, D, E, F, G, it goes 1, 0, 0, 1, 0, 0, blah, 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 blah. Okay?
I took a computer program class. I wasn't very good at it, but
Rock and roll. Well, thank you for jumping in with us today. Okay? So we got binary code. And the reason that computers can talk in binary code is because of silicon. Because silicon is a semiconductor, which means it's really good at sometimes conducting and sometimes not. When it conducts, you have a 1. When it doesn't conduct, you have a 0. If you used instead iron to make a computer, everything would be a 1 because it would always conduct. If you use wood to make a computer, it would never conduct. It would always be zeros. So silicon and germanium are great for making computers, not only because they sometimes conduct, sometimes don't, and you can make them act as switches to talk in ones and zeros, but because we're talking about the size of atoms. So you can make these computers really, really what? Very good. So you think about the fact that when I was your age, when I was sitting in these same seats 20 years ago, 25 years ago, really, we had a computer at home. My computer at home was, I wish I don't really have it, almost as big as this whole box right here. My computer at home was probably about 75% of the size of this big container here. And it sat up on the table, and there was a big giant monitor on top, and it had 2 gigs worth of hard drive. 2 gigs. And man, we bought it, and it was hot. This thing, it would run NASCAR racing like crazy. I could play video games on this thing like, NBA Live 96. I tore up on that computer, okay? In my pocket, I've got 60 gigs. Some of you guys have an Xbox with a terabyte, which is how many gigs? How many gigs is a terabyte?
1,000.
Yeah.
I actually have 6,000. I have 6,000 gigabytes.
Rock and roll. You see what I'm saying? And we can do that because all of the computing power to get those ones and zeros are the size of atoms. And so you say, I hear all the time in this class, man, Mr. Tyler, when are we going to use chemistry? You got chemists working their butt off at these places like Google and Facebook and Apple and Microsoft, making these computers because what they're doing is they're working with these atoms. Okay? I think that might be all we want to roll with. Let me make sure there's nothing else I need to say.
the first computer I ever made was bigger than this room.
Yeah, and like the computer that sent the astronauts to the moon was like the size of a gymnasium, and less computing power than what's in your pocket. Okay.
Say that the computers that were the first moon mission has the same amount of power as a modern day calculator.
Oh yeah, absolutely. All right, rock and roll, guys. So that's pretty much what I want to say today. We'll talk about some more families and groups tomorrow. I want to give you the rest of the day today to work on your element activity. If you have any questions at all, let me know. Daniel, make sure you go and claim your element, and have a great day. If you need anything, let me know. You have a question, buddy?
No, sir, I'm good.
All right. Have a great day, and I will see you tomorrow.